Okay, thanks everybody for joining us today. This is an impromptu workshop that we have organized, taking advantage also of AI stats in Morocco. So some of the people who are here were until yesterday were in AI stats, and some others flew directly from Japan. And yeah, so this is a bilateral workshop between the ELLIS Unit Milan and RIKEN Artificial Intelligence Laboratory. So this is also a workshop is partially supported by a European project, ELIAS, and this is one of the projects that we are involved with through ELLIS. And this is a fairly large European project at 35 institutions from 17 countries. And through this project, ELLIS is partially sustaining itself. In particular, the PhD program and the junior researcher mobility is paid for by these projects here, these European projects. There's a series. They all start with L. There was Elise, Elsa, Elliot, Elias, and they keep help keep ELLIS working. Okay, so the ELLIS Unit Milan is made up of 4 institutions who are represented here. You can see on this map there is this university and Politecnico. They are on the right hand side. They are fairly close to each other. We see each other from across the street from the windows. There's Bocconi, which is econ school in the south, and there's Bicocca, which is another, is like Statale, is a generalist university up north. So this Milan is not very big, but it takes some time to go through from university on another. So we have more than 40 members in this ELLIS unit, and there are 42 units altogether in 17 countries, and 5 of them are in Italy. So besides Milan, we have Turin, Genoa, Trento, Modena, Reggio Emilia, and something I forgot. I told them all. Yes. Okay. So it's 4 institutions, so we have a quite spread of research areas. So there's more, more general, like ML theory, deep learning, and AI economics, and there's others more traditionally applied towards language, vision, but also physics-based ML, neuroscience, and so on. It's so it's a quite diverse setting of research, and to give you an idea, these are the kind of venues we publish on. There's some traditional core ML venues, some traditional theoretical CS venues, and then more venues more in the vision, robotics, and NLP areas. There are already a bunch of papers that resulted from the fact that RIKEN and here I'm just citing those papers between RIKEN and UNIME that I know of, and we work on very similar things, so it's quite natural to have collaborations. So we had an oral paper in AI Stats 2024, and then we have two papers this year, one ICML and one in COLT, that with people from RIKEN and UNIME. So ELLIS Unit Milan is involved in 3 ELLIS research programs. These are thematic programs that are meant to structure and organize and focus the research within ELLIS. So we are involved in geometric deep learning, interactive learning, and in quantum and physics-based machine learning. And what happens in these research programs, and that we have workshops. And we organized workshops in several places, and we had a couple of these workshops at the recent EURIPS meeting in Copenhagen in December. And I take this opportunity to remember that, to let you know that there's going to be another EURIPS in Paris in December. And this will be an official EURIPS location if you don't want to go all the way to Australia, which I think it's the better option for Japan, but for Europe, probably not. And we had an amazing turnout of papers in Europe last year as an ELLIS unit. So we were highly. And what other things we do here? Well, we do research together, and we organize events like this one, but also we have pre-EURIPS events. We had a few of them. The last one, in December, it was in University Bicocca, Milan Bicocca. We organize EWRL. We've organized algorithmic learning theory. We organized the summer school, for instance, the Mediterranean Machine Learning Summer School. And also, we are going to have very soon, so come back, the Reinforcement Learning Summer School jointly between Politecnico and University of Milan. So these are, and then there are several other events that are organized by these four institutions. Some of these events are, most of these events are organized jointly by our institutions. So we share the burden of the organization. Yeah, that's basically everything what I wanted to say. So I will leave. Thanks. And last but not least, I would like to thank Giulia for helping. I mean, for doing the most of the organizational job here. Thanks a lot.
So today, let me briefly introduce our RIKEN Center. So RIKEN Center for Advanced Intelligence Project. But before starting, maybe I have to talk about RIKEN. So RIKEN is a national research center in Japan. And RIKEN is actually not an acronym of English word. It looks like Research Institute for KEN, but actually it's not true. So RIKEN is actually in Japanese, it's called Rikagaku Kenkyūsho. So this means Research Institute for Physics and Chemistry. But this is too long. Rikagaku Kenkyūsho is too long even for Japanese. Then we prefer to shorten it as RIKEN. So RIKEN is actually a Japanese acronym. But maybe some time ago, RIKEN was still called Research Institute for Physics and Chemistry or something like that. But in the last 30 years or so, we have many different areas like medicine, biology, supercomputer, and our AI center. So it's not Research Institute for Physics and Chemistry anymore. So then at some point, the RIKEN headquarters decided to use our Japanese acronym, RIKEN, as our official English name. So that's the most important take-home message today. RIKEN is not an acronym, but it's our official name. So RIKEN actually has a relatively long history, started in 1917, but in Italy, maybe 1917 is quite new, but in Japan, it is quite old. So it was actually started as a private foundation. Even like emperor's family donated some initial funding. So then after that, so RIKEN did a lot of research on physics and chemistry, and it was actually quite big. It was called RIKEN Concern, and they had 63 companies and 121 plants. So it was a big entity, and it was quite successful actually. But because of this big success, RIKEN was regarded as a kind of dangerous entity. And after the World War II, it was unfortunately broken up. But then in 1948, RIKEN restarted as Scientific Research Institute. And then since then, it became finally National Research and Development Institute. We are under the Ministry of Education in Japan, and it's purely public research institute nowadays. And we had 2 Nobel Prize laureates and also 1 Nobel in physics and 1 in chemistry. So then now RIKEN has 4 research domains. So they are called physical science, sustainability science, life science, and mathematical, computational, and information science. And we belong to the last one, and our Center for Advanced Intelligence Project is included here. Then what is RIKEN AIP? RIKEN founded our Center for Advanced Intelligence Project in 2016, 10 years ago, as a research institute for a national project run by the Ministry of Education. Then actually just last March, we completed our 10-year project. Then we are just starting the second phase of AIP. So we became a kind of permanent center in RIKEN, and we hope to contribute to this community for a longer scale. Now we have 117 employed researchers, and about half are international researchers and about 20% are female researchers. So it's quite diverse in Japan. Then we have more than 240 visiting researchers, mainly from universities and also some from industry. Then we have about 100 domestic students as part-time researchers. So they are mostly PhD students. Then finally, so we are running an internship program from the beginning, and we have accepted more than 240 students so far. So every year we accept maybe 20, 30 students. So during the COVID time, so we couldn't run the internship program for 3 years or so. But after that, we resumed the program and it is working quite well. And previously we had some internship students also from Italy, but through this workshop, so we hope to get to know more each other, and hopefully some of your students or some of you are interested in coming to Japan in the future, in the near future. Then, so we are located in the center of Tokyo. Actually, it's 10 minutes walk from the central Tokyo station. It's really in the center. But at the same time, several teams are distributed in different universities, like Sendai, Nagoya, Osaka, Kyoto, Fukuoka. So depending on the teams, so they are located in different venues. So then from this April, so we started the second phase of AIP, and we restructured a little bit, and now we have 3 research groups. So they are respectively called mathematical intelligence, domain intelligence, and physical intelligence. The mathematical intelligence group is something like machine learning people. So we try to understand the state-of-the-art machine learning technologies and try to create new concept for high reliability AI. Then the second one, domain intelligence. So they try to develop AI technology specialized for domains such as science and industry. So nowadays, our main focus is, of course, AI for science. So RIKEN has a lot of strong physics centers, chemistry center, biology, medicine. So we are collaborating with those people and try to push AI for science strongly. Then the last one is a new project. So it's called physical intelligence. So we try to develop AI technology adapted to diverse data from the physical world. So we also included some robotics people and more like physical contact people and try to merge AI technology with real world sensing. So that's a new challenge, and we are trying to acquire big funding now from the government. And hopefully after getting it, we really try to kickstart a big project. Then, so these are teams. So some of the team leaders are coming this time, team directors are coming, and they are mostly from mathematical intelligence this time. But we also have people from domain intelligence and physical intelligence. And in domain group and physical group, we have some like applied people, but still half of them are more fundamental and machine learning oriented people. So they try to bridge different groups. But in the first group, mathematical intelligence group, so people from math, computer science, physics, and so those people are discussing together. Then, okay, we had some nice results in AI machine learning technologies, but maybe I don't really have to go into the detail today, but we do machine learning study for foundation models and sequential decision making, multi-level optimization, and things like that. So these are, I think some topics are quite common here. So hopefully we can discuss a bit more about it. Then, so AI for science part. So some teams are working on basically earthquakes. So long time ago, historically, people worked on like finite element method. So they used a grid and try to numerically approximate the properties. But now people use a physics-informed neural network and have continuous approximation of the entire solid state. So then, so we can really solve an inverse problem in a nice way. Then some people are working on so it's actually selective inference topic. So in data-driven science case, so we use same data for generating a hypothesis and then evaluating this hypothesis. Then the standard statistical test is biased. So we want to overcome this issue based on selective inference. And we had already nice theoretical results and also software there. Then application in medicine. So it's clinical application of ultrasound diagnosis support system. So we started this project quite a long time ago. So just the beginning of AIP, so maybe 2016 or 17. Then in the first few years, we had already some technological results. Then after that, so we included the company and we tried to obtain approval from the government. Then finally, so recently it was approved, regulatory approval, and we have AI-equipped medical device. So hopefully this will be really installed in the real hospital. Then the last one is about global 3D land cover mapping. So this is one of the challenging topics because already some like 3D land cover maps are available, but they are mostly commercialized and it's not open to the public. So we want to achieve the same thing essentially in the completely open domain and field. And we could achieve this, so based on some nice technologies. And also we had a paper at NeurIPS 2 years ago. Okay, good. So maybe I don't really have to go into the technical details today, but so we have broad topics and hopefully some of the topics matches one of the your teams, and then we can really discuss more challenging future topics together. So I'm looking forward to having this workshop. Thank you very much. So again, it's me. So the previous talk was by center director, but I'm also having a team in RIKEN AIP, and I will talk about our team's research. So the title is about reinforcement learning, but in the end, I decided not to go into like one topic in detail, but rather I want to showcase some of our previous achievement because this is the first time, and it's nice to like expose some of our experiences and hope that we can find some common ground. So just self-introduction. So I'm director of RIKEN AIP, and also I'm professor at the University of Tokyo, and also I'm supporting some local startups in Tokyo. Then my background is machine learning theory and algorithm. So I'm rather hesitated to say I'm doing theory in front of Nicolò, but still slightly more theory side. And usually I spend, let's say 10 years on one topic and publish a book. So we did something on machine learning in non-stationary environments, density ratio estimation, reinforcement learning. So this is a textbook, variational base, and more recently, machine learning from weak supervision. So these are like our achievement in the team. So then potentially we are also interested in applications, but this is way beyond what our team can do. So we always try to find collaborators outside in companies and other research centers and try to do different applications. We just helped those projects. Then, so okay, I was actually program chair for NeurIPS AI Start, and so AI Start is one of my favorite conferences, by the way. And also now I'm a board member of ICML. Then, so let me briefly talk about our machine learning research from imperfect information. So this is the main theme of our team. It's a high-level overview. So, okay, reliability of machine learning system is quite important, and it depends on the quality of training data. So weak supervision. So training data may contain some insufficient information. I will say, so what I mean by insufficient. But one typical setting is in binary classification. So we, of course, need positive samples and negative samples. But sometimes we only observe positive samples and unlabeled samples. So it's called PU classification. But still, we want to solve a classification problem only from PU data. So that's one like standard setting. Then label noise is another challenge. So labels are prone to observation error or human mistakes. So we want to overcome it. So we have like a lot of flippings like this. Or distribution shift. So this is one of the topics I've been working for more than 20 years now. So training data and test data have different distribution, and we want to somehow adjust the bias caused by the changing distributions. So improving the reliability of machine learning systems is a long-standing challenge, and we've been working on this topic for many years. Then weak supervision. So already we know that so supervised classification is working superhuman nowadays if you have a huge number of samples, like in speech, image, language, etc. But as I said, in RIKEN Center, we have some application research, like in medicine, so natural disasters, robot control, brain signal analysis. So in those domains, so still collecting big label data, high quality big label data is not straightforward. So ideally, we want to say, okay, machine learning from small data, but learning from small data is not always possible. So we have larger variance. So instead, so we still need big data, but we hope our big data is somewhat cheap and low quality. So we don't really assume we have high quality big data, but we have some kind of low quality big data. So that's weak supervision. And as I said, so PU classification is one of the typical examples. So today, actually, so for this talk, I didn't really bring any technological slide. So I don't really show how to solve it, but we can estimate the classification risk only from positive and unlabeled data in an unbiased way. So then we can basically solve PU classification problem. Then later we found that the same technique can be used for solving many different weakly supervised learning problems. Maybe the second one is actually quite interesting. It's called unlabeled classification, UU classification. So now we have no labels at all, but we have instead two sets of unlabeled data. And our assumption is that class proportions are different in these two sets. So let's say in the top left data set, so positive and negatives are, let's say 60%, 40%. Then the second one has, let's say 20%, 80% or something like that. Then only from two sets of unlabeled data and class priors, we can solve a classification problem. And basically we can show the kind of same convergence rate as the standard supervised learning case. So this is actually a quite nice formulation. Like, let's say there are two hospitals and each hospital has so many medical images, but doctors are so busy, so all the images are not annotated. But suppose we have some prior knowledge that in hospital A, so we have 20% cancer patient, and in hospital B, we only have 10% cancer patient or something like that. Then in principle, from that information, we can train a classifier. And given a new medical image, we can predict whether cancer exists or not, without having any single annotation. So that's UU classification. So then also learning from similar dissimilar data. So this was done by Bao when he was a master student. So we had a lot of variations. And also we have multi-class extensions like noisy labels, ambiguous labels. So these are included here. Then, so this is basically empirical risk minimization research. So we can apply the idea to any loss function, classifier, optimizer, regularizer. So it's quite generic. And we published a book on this 4 years ago. So this is strong coffee and weak coffee. So it's weak supervision. Then after that, so we are still working on this topic, and we have a mathematically unified framework, and also new problems, new algorithms, and also some applications in like speech denoising, reinforcement learning, imitation learning, and also LLM alignments. So these are quite nice applications of weakly supervised learning. Then the next one is label noise robust learning. So output noise is everywhere. So in one-dimensional regression case, so we have input X on the horizontal axis and output Y on the vertical axis, and we have some noisy outputs, Y bar. But usually we don't care, right? We just fit our predictor to noisy labels. So we just minimize the squared loss between our predictor and noisy output. And in the regression case, maybe this is fine. So as long as noise is independent additive, mean zero, then so we can have consistency from noisy output. But in the case of classification where labels are flipped, so this is not straightforward. So it's a classic topic, but in classification, actually, we need specific noise reduction mechanism to achieve consistency. We can easily have some example where classification is not consistent. So we need to explicitly reduce noise in some way. Then, so in our team, so we focus on the approach based on so-called noise transition matrix, T. So in the 3-class case, it's a 3x3 matrix. And ij element means basically label I is flipped to label j. It's the probability here. And once we know this noise transition matrix, so we can reduce the bias, eliminate the bias caused by noisy labels. But the issue is that we need to know the T matrix. But this is unknown, so we should estimate it from data. But estimation of T only from noisy labels is not actually solvable. So T is not identifiable, unfortunately. So then, we have to spend some time to think about adding some bias, like using human cognition properties. Or we try to do some mathematical tricks to reduce the estimation error. And also we try to learn T and classifier at the same time, avoiding two-step procedures. Then finally, we had a reasonable estimation method to estimate T. So I don't really go into the detail, but so in the 3-class case, so actually true noise transition matrix T can be described as a triangle. Then all noisy data points actually live in this triangle. And we want to recover this triangle. Then basically, so we try to have a triangle that contains our all noisy labels inside, and the volume is minimum. Then, so under some weaker condition, we can show that so true T can be recovered by this algorithm. So this is one of the most generic approach to estimate the noise transition matrix in this community. But the problem is, so the discussion so far was so-called input independent label noise. So we only consider the flipping from class I to class J independent of input X. But the real world noise is almost always input dependent. Like we have more noise near the decision boundary and we have less noise far away from the boundaries. So it's input dependent noise. And this input dependent noise is much harder to solve. And we are still working on some of the new methods on this. Then finally, distribution shift. So training and test data follow different distributions because of changing environments over time or some kind of sample selection bias due to privacy considerations. So we want to train a test domain predictor using training data from different domains. So that's what we want to do in domain adaptation or transfer learning. And this is actually at all new topic. So we organized a workshop already 20 years ago at NeurIPS. At that moment, there was no name for this problem. And our workshop was entitled NIPS Workshop on Learning When Test and Training Inputs Have Different Distributions. So this clearly explains the problem. And it was actually quite successful, and we had a lot of great speakers and participants. Then after a couple of years, we had the edited volume from the workshop. And here we named it the dataset shift in machine learning. But unfortunately, this name, dataset shift, did not become popular, and people completely forgot it. But interestingly, because of this LLM hype, so new names appeared, and now it's called distribution shift or fine tuning or whatever, a lot of new names. And in the last 5 years at NeurIPS, there were workshops on distribution shift, fine tuning, or reliability, something. And so this distribution shift research is back again, and it's becoming more important nowadays. So classically, we worked on the problem called covariate shift. So only input distribution changes. Like this is one-dimensional regression, and we have a common true function red one. This doesn't change, but only the location of input point changes. So blue points are training, and black crosses are test data. And from blue, we want to estimate black. So that's the covariate shift problem. But if we just use linear least squares, for example, then we end up in fitting blue points and just having green line like this. But once we have importance weighting, so then only from blue points and importance weights, so we can recover this green line and we can fit black crosses reasonably well. And we can show this is consistent. Then, so we spent some time to estimate the importance weight from data, not estimating two densities separately, but try to directly estimate the ratio of two densities. So that was a kind of classic topic, and we had some research on this. Then more recently, so we are extending this scenario to online learning. So now, so it's changing over time, sequential distribution shift. And we have a basically online convex optimization style algorithm to follow the changing distribution. Then now our target is joint distribution shift. So in the covariate shift case, only P of X changes. But this is a very strong assumption. And also there's no way to confirm that so the current shift is covariate or not. But once we allow like joint distribution shift, P of X and Y changes, then this is the kind of most generic setting. And we want to really solve this problem. And we had some like initial solution to this problem. And we hope to extend this part a bit more. So now we can also handle out of distribution scenarios. Then we have nice applications in LLM alignment and also test time adaptation these days. Okay, then finally, let me briefly talk about reinforcement learning, because okay, these topics are also quite important in reinforcement learning. Like so current bottlenecks of reinforcement learning is to design a good reward function. So this is always a big challenge. And learning reward function from demonstrations by inverse reinforcement learning or imitation learning. So these are standard approaches. And we can naturally extend those classic approaches to like weak supervision and noisy supervision. So we can basically apply our previous results to the framework of reinforcement learning. Then reward can change over time. So this also happens in many real world problems. So this is exactly the distribution shift problem. So we can apply distribution shift adaptation in reward modeling with application in LLM alignment. Then also rewards are not necessarily given immediately. So that's another sparsity of reward, because at every time point, maybe we don't really observe immediate reward, but at some point, at some like time interval, we only observe a reward value. Then we want to kind of redistribute this like reward value to each time step to apply a standard reinforcement learning technique. So this can be actually nicely done by our transformer. So it's called reward back transformer. Then, so more recently, so we are interested in aggregation of reward values. In standard reinforcement learning, so we just use a discounted sum. So we add immediate rewards, and we want to maximize the sum or discounted sum. But depending on the application, other than sum is useful. Like in the case of drug discovery, for example, then maximum reward in a certain interval is actually more important than like everyday measurement. Or in portfolio optimization in finance, so-called Sharpe ratio is a standard metric. So it's mean normalized by standard deviation, because people care more like reliability. They want to avoid risk, so they want to normalize by standard deviation. So to handle this kind of slightly different aggregation way, so we want to generalize the methodology. But even in this simple MDP, so if you just take the sum, then policy 1 is the best. But if we take the mean, then policy 2 becomes the best. And max, so policy 3 becomes the best, or something like that. So the way of aggregating rewards is really important in choosing the best policy. So we want to have a kind of unified framework to handle this kind of generic reward aggregation. Then basically the key is the recursion. So the discounted sum can be recursively expressed in this way. So this is nothing complicated. It's just sum of R1 to, from R1 to infinity. So then we just take R1 and then sum from R2 to infinity. So this is a recursion. And basically reinforcement learning just utilizes this recursive form in the Q function, the V function, advantage function. And we generalize this. So now, okay, we initialize tau 1. Then update part is a recursion. So tau t minus 1 and new reward RT. Then we obtain tau t. So this is the update part. Then finally, so tau is post-processed and we obtain the final output. So this is a generalized expression of the reward aggregation. And naively, so discounted sum can be expressed in this way. So we just initialize it with 0. Then given previous tau, so we multiply it with gamma and add new R, new reward, immediate reward. This is our update function. Then post-processing is just identity mapping in this case. Then we can recover the original discounted sum. But now, so we can actually have a reinforcement learning algorithm for this generalized form. Then this contains a lot of interesting expressions like discounted mean, discounted max, log sum x, range, mean, variance, top k. So these are all included in this framework. And we don't really have to change the framework, but we can just apply and consider all different way of aggregating rewards in the same framework. So then, so I don't have time, so I just don't go into the. So we have a like Q learning, extension of Q learning, PPO, TD3. So they are naturally extended to include the generalized form. So I just skip experiment. Then, okay, one more slide about future challenge. So now, okay, we have foundation models here and there. And like classically, so people just use the common foundation model. But nowadays, this is more personalized or specialized to each task. Let's say I'm here, then I use my mobile phone and let's say download a common foundation model in my mobile phone. And I communicate with my AI system. Then, so over time, the environment is changing. So this is a kind of natural learning paradigm in dynamic environments. I mean, this is an extension of standard like online learning, continual learning ideas. But now, so we have human AI interaction here. So things become a bit more complicated. Then in addition, so we have a large number of humans and also a large number of tasks, a large number of modalities. So we have learning in diverse environments. So here are topics like multi-agent learning, multi-agent interaction, multimodal learning, task learning. So these are quite important. Then also, so we need to care privacy preservation or some adversaries in the system or fairness kind of issue is also important. So because the system is quite big, so it's a society level, so we need to really care this kind of societal problems at the same time. Then finally, so due to this size scale, so we need to take care of computational efficiency and energy efficiency. So from the theoretical or algorithmic viewpoint, it's not that easy to directly work on energy issue, but still, so by improving an algorithm, hopefully we can contribute to like save energy in this kind of system. So in particular, so we have a huge number of different models, but they are quite similar to each other in many cases. Or in some clusters, they are quite the same. So hopefully we use that kind of structure into account and try to have a quite efficient system. So in terms of distributed optimization or some kind of compression. Then in RIKEN, so there is a quantum computer center, and already they have 3 different quantum computers, and they try to combine quantum computers and also GPUs, hybrid ones. So we are a bit apart from that center, unfortunately, in terms of research, but hopefully we can also take into account such new computing paradigms in this kind of system. Okay, so this is the end of the talk. Thank you very much.
Are there any questions?
Thank you very much.
Thank
very
you.
Impressive, the amount of application that you studied. Because of my main research domain is healthcare, I would say medicine. I wonder about the data shift that or distribution shift, whether you have occasion to apply to study into the healthcare, which is really an elective domain for such a problem. Thank you.
Right, thank you. That's quite important. So when we apply distribution shift research techniques, then always the identification of the shift type is the biggest issue. So if we know it's covariate shift, we have already reasonable methods. If it's a label shift, we have another method. But identification of the shift type is a kind of unsolved problem. So that's why we are interested in joint distribution shift. But this is the kind of most generic way. And once we have a reasonable solution to this problem, then we should try this method first and see what kind of shift is happening behind. Then once we identify the shift type in a reasonable way, then we could use more complicated, sophisticated method to improve the performance. So still, it's an ongoing scenario, but I think we have a lot of common issues, and yeah, hopefully we can have a bit more discussion about application of distribution shift research. Thank you very much.
Yeah, and once you talk about distribution shift, and then you say, okay, let's look it in the online model, and then you talk about online convex optimization, it's like that's the perfect model for, it's oblivious to any assumption on the environment. It can deal with anything. So to what extent you exploit the fact that you indeed have a distribution, but you're using online convex optimization, which is generally oblivious to that?
Yeah, but still, like for the distribution shift type, so we assume it's covariate shift, a label shift.
Okay.
Then based on that, we estimate the importance weight.
Okay.
If we can handle a joint distribution shift in that scenario, then already that's a very generic scenario. But then we need actually some label data from the test domain.
Right.
But this is something we want to avoid. And we want to somehow mitigate this issue by applying weekly supervised learning in that scenario. So these are ongoing challenges for us now.
Okay. Thanks again. Thank you.
So I'm Masaaki from the RIKEN and IF Tokyo. Then today I'm going to talk about a very kind of a high-level research topic from my group and my personal research. The title is that like a dynamical analysis for the deep neural networks and the transformers. So anyway, I guess that because of time limitation, maybe I'm afraid of that I cannot mention the transformers anyway, but I try to do my best to present everything here. Anyway, the background is like the emergence of the deep learning and also like artificial intelligence. It's really like a fancy technology, and I believe that all of us are really interested in the kind of really the new technologies. And my interest is that kind of like not at the engineering side, but for the more like the science side. I try to like understand the kind of the new phenomenon, and there are many like new interesting phenomena appeared from the AI technologies and like scaling law or like emergence of the intelligence. Like and there's many new phenomena, and we try to understand the what is inside and what's the mechanism of these like interesting points. So. And then again, I try to back to introduce the very kind of the conventional, classical, but still like an interesting question. Like we try to understand the like what the inside of the deep learning and the like artificial intelligence. And this is a very typical question, somewhat old question, not so modern, but I think this is still like an interesting question. The one typical question is that like why deep learning does not overfit to the training data, and it's raised this question is raised by the very famous paper around the 2015 or 14. But anyway, we can easily observe that the like actual phenomenon of the deep learning is like really does not fit to the classical theoretical analysis for the data science, including the statistics. Like typically, for example, meaning 20 years ago, we believed that like the larger models are harmful because of the overfitting. So and there are too many parameters, and the model easily fit to the training data, and they cannot do the nice prediction. So so in that sense, like we believe that the error can be proportional to the parameters of the data size. So in that sense, like we have to avoid the larger models. But as we know, like recent deep learning has many huge number of parameters. There's still a very contradiction between the theory and the phenomenon. So in that sense, we have to improve the theory to understand, describe this kind of like a real success of the deep learning and like emergence of the artificial intelligence. And I believe that still like it's kind of classical, but still very interesting and unsolved question. So I also I briefly mentioned like one unresolved question from this research field. Like typically like as I said, like overfitting is still like unsolved question, as I believe. So and in my understanding, there are some more many the thousands paper has been published to explain the phenomenon of the overfitting of large models, but still there's many unresolved questions. I mean one of my reason from my understanding is that deep learning is really complicated. It's a very complex phenomena, and a mathematical description on this phenomena is we did a very great job, but not as powerful to fit to the real phenomenon. So in that sense, we have to do some approximation or more not precise evaluation or inequality or order-based analysis. So and there are many great theories, and also I wrote many papers using kind of such theories. But anyway, so I believe that this is not as powerful as expected. So yeah, first there are great theories and many development. So anyway, that's the kind of not as precise as expected. So that's kind of limitation. Yeah, there are still some gap between the theory and experiment. And the very famous this paper pointed out that kind of the overfitting, it cannot be well explained by the current study theoretical analysis. So that's kind of the sorry, too close or too far? Sorry. Too far. Okay, I mean. Okay. Okay. Anyway. So okay. What I said. Anyway, so I explain kind of current limitation or many technical challenges, and some of them are very successful, but are not as powerful to perfectly describe the overfitting in my understanding. So, and here, key is kind of like a dynamical aspects of the many aspects of training neural networks. So, and many theory has based on the more static case, focus on the empirical risk minimizer, or kind of like output of the gradient-based stationary points achieved by the gradient-based algorithm. But it is kind of not as far as expected. So, and instead, we are focused on the dynamic aspects of the training, we constrain the SGT dynamics, and they try to precisely track the behavior of the output algorithm and try to achieve the more precise detailed information of the trained models. That's kind of the overview. So, and it is also pointed out that dynamics can be a key to understand the deep learning. So as long as we use a static analysis, so we do not specify that, we cannot specify that which parameter is to be learned. So that's kind of one limitation. So to resolve, to avoid the issue, we have to use some kind of a uniform based analysis, the size of the overfitting is upper bounded by the worst case value of the generation gap. And it is a very general and very nice theory, but not so effective in the real deep neural network. So instead, we try to describe kind of the precisely describe the dynamical trajectory of the algorithm and try to achieve the more precise information of the trained algorithm. That's kind of overview and the importance for dynamic analysis. So, and of course, there are many studies, many studies to track the dynamical behavior of the trained neural networks by using statistics, statistical physics, or statistical mechanics. So, and the key point is that high dimensionality or large scale limit can be a key to describe the macroscopic properties of the training process of the deep learning. It means that and there are many parameters, but we don't have to track every parameters one by one. So what we need instead, is kind of a macroscopic behavior. What is the mean? What is the variance of the parameter value of the neural networks? That's kind of our goal. So in that sense, we don't have to. So instead we consider the high dimensional limit. So in physics, we say that sometimes limits and try to describe a more rigorous description of the distribution of the parameter values. It's kind of the one a challenge, one way to achieve the precise information of the deep learning dynamics. So, and it's somewhat I've seen that if in the kind of nice case, sometimes the distribution have a Gaussian distribution, and as we know, Gaussian is a very simple distribution, a mean and variance are sufficient to track the whole shape distribution. So in that sense, it's only a two-dimensional parameters. In that sense, it's very easy to track the time evolution. It's kind of a key to use high dimensionality to get some precise analysis. So, and we expect that a precise analysis can cover kind of a downside or a limitation of the classical theory. It means that as long as we use static analysis, the data error can be evaluated by kind of the inequality or order analysis. But if we have the more precise value, so we can rigorously describe what is the what the loss value or the error value, and it's not effective to analyze kind of the mechanism of the deep learning mechanism. That's kind of the our overview. As we know that the neural networks or artificial intelligence are too complex, then it is not well precisely studied by the order of analysis, but instead precise-based analysis can be useful and the key to improve our understanding. So that's kind of an overview of here.
Maybe the right-hand side looks more challenging.
Oh yes, yeah, but we did it. So, and I will describe the result in next 10 minutes. So anyway, so I skipped here, and okay, so I tried to explain one of our recent work. It's kind of a precise gradient descent training dynamics for the high-fidelity multi-layer neural network. It's open in this archive preprint. So, and I spent 3 slides for setups. That was very general. So we consider a deep neural networks L depth, and width is a Q, and the feature dimension is M, the dimension of M. Then we have many layers, and L can be more than 2 or 3. So like a finite, any finite L is okay. And this is like our unit network model. So yeah, and input is X, and the W is like a weight parameter for each layer. Then like a weight parameter activation, simple activation, the weight parameter activation, and we put it kind of the composition of this model, and we have this like neural network model. It's very general, fully connected neural networks. So, and setups are also very simple. Training setup is simple. So we consider that squared empirical loss function like this. Then, and so we update that every parameter from every layer by simple gradient descent like this. And for each t, so the new parameter is given by the current parameter minus learning rate times gradient. It's very simple, the simplest case in machine learning, I believe. So, and our analysis is like this. So we try to understand, describe like a generalization error. It means that, so okay, we have the parameter WT after T update. Then this is like and also we consider a new sampling of the X and Y. Then we consider the expectation of the squared loss. It's kind of like a very classical setup. Then, so this is our generalization error. So this is our target. So, and our goal in this paper is that we try to specify that this is the value, exact value of this limit. It means that we constrain this high dimensional regime, like a sample size n and dimension m diverges to infinite while preserving this ratio, like m over n converges to some finite constant. So, and we constrain this limit, then we try to achieve this value. And of course, I have to note that this is like we need like exact value, not an order and not like inequality based. So we need the exact value. That's our goal here.
You increase the input dimensionality.
Yes.
Neurons.
Yeah, yes, in the input layer, like a parameter diversity to infinity.
How about the depth of the neuron?
Depth can be fixed, infinite fixed, like 10 layer or 20 layers, okay.
Only the bit.
Only bits. And the sample size of bits, yes. So, and our approach is follows the like a high dimensional approach as I described before. So I really briefly outline our approach. And first one is that we can, so even though we have the many, almost infinite number of the parameters or the feature vectors, but we can represent it like a macroscopic behavior by using the kind of like elemental distribution representation. It means that, so if you have the very high dimensional vector that is very large, but we don't have to like track the one by one, this value one by one, and we can represent this high dimensional vector by this like empirical distribution like this, kind of like just reform this vector to measure. Then, and if the in the main in nice case, if the dimension d diverges to infinite, so this distribution can be converged to some Gaussian or some related distribution. It's very simple, overview of the approach. Then we use the kind of like dynamic analysis by using the distributional presentation of the neural networks. It's kind of like our approach. Okay. So, and because of time limitation, I skip time in technical details, but I already put some like existing studies. So, and we have in these 10 years, there are many new theories to achieve the precise analysis for the dynamics of the deep learning. And one of the most famous ones is neural tangent kernel (NTK), and the more neural and also mean field analysis. And in these 5 years, the neural one is like a dynamical version of the mean field analysis and also tensor programs. And the difference is that whether they can achieve they can analyze the feature learning and whether they can achieve the deep layers. It means that the standard old theories can handle the shallow layer, like only 2 layers, or it can achieve like a more depth layer, but they are more lazy regime. It means that many layers can be essentially fixed, and the last layer can be activated. That's like a lazy regime. And the new theories can handle the more feature like a non-lazy regime and the deep layers. But the limitation is that it's more like the physics based and not so mathematical rigorous. And another point is that this is a more general thing. But one limitation is that they specify the value of the deep layer after many updates by some equation. But solving this equation needs exponential time. It's kind of like another limitation. So And we tried, it's kind of like very difficult to apply this approach to the more like, longer training dynamics. So in that sense, we try to resolve the downside of the dynamical studies, and we try to achieve this field. That's kind of our goal.
So, along the vertical axis, so linear model is one layer.
You see that, yes.
Maybe you observe significant difference between one layer and two or more layers.
Well, I mean, it's, yeah, actually, almost yes. And the the slight difference is the two layer is also like very somewhat easier to analyze. So because like
big difference in 2 and 3 or more.
Yeah, yes. I agree totally with this. That's fine. So anyway, so and my question is that is it possible to analyze the dynamics of the deep networks more than 2 layers, 3 or 4 or 5 in the real situation with reasonable computational complexity. So that's our goal. So, and our approach is it's kind of application of the very celebrated theory of the high-dimensional statistics and all of the field of physics. And the notion is like a state evolution with correction. It means that state evolution is like a sequence of the distributions which specify the kind of time evolution of the distribution, which is like an element distribution of the kind of neuron or like a feature vector of the neural network. It's kind of like a one point. But the technically difficult point is that so we simply apply the existing separation theory to the deepness, but the distribution is very far from Gaussian as after many updates. It means that at the initial point, many neurons or feature vectors has followed the Gaussian distribution, elemental distribution of the feature vectors for the Gaussian distribution. It's very easy to analyze. But after many updates, they can take a more like a heavy tail and come to non-Gaussian, and they're mathematically hard to track the dynamics because of the time correlation. It means that if we after many updates, we reuse the data many times. So there are many strong correlation among the elements of the neurons or the feature elements and feature vectors in the deep network. It's kind of like it can violate the condition to for the a central limit theorem. In that sense, we cannot use a Gaussian representation. So, but the one a very famous paper suggested that there are some correction term named the onset correction. So it can reduce estimate and the time correlation, and the putting the correction term to the algorithm can reduce the correlation. And after correction, so for every time t, so we can enjoy the Gaussianity of the limited distribution of the Gaussian neurons of the deep network. It's kind of like a key technique here. And yeah, this paper is kind of suggested that this point for the linear regression. So then we apply this approach to the deep neural networks. Yeah. So many time is very close, and I'll skip the several slides. But anyway, so this kind of the overview. So and here we considering like a deep neural network. Then we considering many neurons or temperature values for each time. Then we first we put some correction and make the correct version of the variables. Then we considering the central limit theorem, then achieve the Gaussian form. Then after that, so we throw back this Gaussian to the original algorithm because this is a corrected version, but what we want to study is an uncorrected version of the gradient descent. So in that sense, we start with here. Then as a proxy, we considering the corrected version of the activation, then achieve the Gaussian, then throw back to the Gaussian to the original gradient descent. It's kind of our strategy here. So then I speak the main part here. Anyway, and then so this is a mathematical formation of the full description of the mathematical formulation of the generation error here. So anyway, so we first calculate the onset correction here, then specify the corrected version of the activation value here. Then by putting this kind of correction term with some bias term with correction, then achieve the Gaussian here. Then we throw back the Gaussian to the uncorrected version of the limit. It's kind of our strategy. So anyway, so and this is our main result. So with some conditions, we show that for each time t, so this is kind of a theoretical value of the generation error by gradient descent. So and this term, the theoretical value as described in the previous pages. So and this value can be calculated only with the training data. So in that sense, we can say that the value of the generation error can be specified by this value, the theoretical value, and it can be easily corrected or calculated. So, and also, it's only with the training data. So, and also we also mentioned that this value can be calculated by the polynomial time in t and the training update. So anyway, so in that sense, we can specify this value theoretically by this form. So this is the experimental result. So, and we compare the theoretical value and the experimental value. Like theory is our output of our theory. And with 2-layer and 3-layer, so 5 layers. So, and after 100 updates, so, and we can save up to 70 updates. So, and maybe we can agree that there's kind of a nice agreement between the theory and estimated version of the actual values. In that sense, we believe that we succeed in specifying the generation error value of the deep neural networks more than 2 layers. Anyway, so this is a first update, but the limitation I stop here. Anyway, so we believe that early studies here, for the mini updates and for deep layers, and we can specify, we achieve a mathematical form of the generation error of the trained neural networks only from the training data. So that's kind of our achievement here. Anyway, that's my talk. Yeah, thank you for listening.
How does it depend on the number of layers?
Layers.
Yeah, because that's one of the main things, right? Yeah.
How depends calculation time or a value of the error or which is your interest?
No, yeah, I mean, it doesn't. The number of layers doesn't appear in the formula of the theorem.
There appears. So, of course, I mean, well, okay. In the this recursive form, so the here and I mean this term, the real updates, real form of the theoretical values are very complicated, and this value is longer affected by layers. Anyway, so and if the many layers, this calculation is this calculation depends on the number of the layers, and it changes by the number of the layers.
Okay. So the order is the same.
Okay. Calculation or order.
Final result. Yeah.
Okay.
Order expressions.
This is just I mean, just kind of the error between the estimation. Okay, here. Okay, the affects. So this concept C implicitly depends on the many parameters or layers or the width of the deepness, but we don't specify C here.
So because if number of layers is too small, maybe the error is large, and if it's too large, also the error is large, and you may want to find somewhere in the middle. Or
and I mean, so okay, so M is a sample size, and M is an input dimension, and N and M has a proportional, they are same order.
Yeah.
So in that sense, N is large and M is also large. So and if you have the if we consider the infinite width, and these values are completely same. So.
Doesn't depend on the number of layers, you mean?
And in I mean, this value depends on layers. Its convergence rate also depends on layers. But but as long as the L is finite, and this result holds.
Okay, let's continue offline.
I see. Yes, anyway.
Okay, thanks again, speaker.